right, welcome to Mount Wilson and the historic 60-inch telescope. We are rotating the dome right now, which is that lovely squeak you hear behind us, or I suppose around us, because we are getting ready to change and find our first target for the evening. So welcome to Mount Wilson, now that you can probably hear me better. My name is Dr. Jenny Krestow. I am a professor of astronomy and physics at Glendale Community College, and I am joined this evening by 4 other astronomers up here in the 60-inch telescope dome at Mount Wilson. And it's not quite dark yet. So we're starting at 8 o'clock, we end at 10 tonight, and it is not really dark enough to do a lot of observing. So believe it or not, we're gonna start this evening with something a little different. If you've joined in the last few virtual star parties that we've had, we always start with a target in the night sky, but we're gonna start with looking at our targeting device, I guess, which would be our telescope. So joining us this evening, we have Dr. Christopher Burns, who is an astrophysicist at the Carnegie Observatories, and Mr. Tom Meneghini, who's this CEO? Executive Director of Mount Wilson. I was supposed to say, hang on, it's not CEO, but he's like the chief guy up here at Mount Wilson. I believe King of the Universe is also a moniker that's known for him.
Galactic Overlord.
Galactic Overlord, that's it. And then Mr. Richard Bell is sitting here beside me at the controls.
Hi, everybody.
Just so you know, all of us are educators. We are all fully vaccinated. We've all had both our shots a couple of weeks ago. So if you're wondering why we're not masked, it's because we are, I don't know, technically outdoors. We're open to the elements, if you would, and we are feeling really happy to be able to join you this evening without masks on. So let me go over to our roving view. Oy, 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 that is not the view we want. This one. So this is the roving view, and it says Barbara on it. So we need to spotlight a different view. Spotlight for everybody. There we go.
There we go. Okay.
Are we live then?
Yes.
Okay,
Yes.
like Jenny said,
We're going to start off looking at the telescope. And this is the first time we've done it with me in front of the camera. So let us know if you don't hear me, because it's hard for us to test the audio ahead of time. But if there's a problem,
You're freezing.
I'm freezing.
Yeah. Oh, now you seem to be back.
I'm not frozen.
Oh, there you go.
Yeah, you seem to be okay.
All right, okay. So hopefully if you don't hear me clearly, just let us know in the comments and we'll try and fix that. But here is our telescope. You can probably tell it's pretty big. It probably doesn't fit on the entire view that we are broadcasting to you. But Tom is the cameraman and he will try his best to pan up and down and look at the things we're trying to see. So this is called the 60-inch telescope at Mount Wilson. And the reason it's called the 60-inch telescope is because this dimension down here is where the primary mirror of this telescope is, and it is 60 inches across. And this was the first nighttime telescope to make its way up here onto the mountain. Prior to this, we started up here in 1904, and that was all solar astronomy. So we had one telescope called the Snow Telescope, and it would study the sun. Then they built a tower to do the same kind of thing, and also built this telescope. And this is kind of, as some of us try to say, this is the grandfather of all reflecting telescopes, because it was the first one that was put into use that worked really well. And it's different than the telescope you may think of. When we say telescope, you may have in your mind, oh, that's the thing that Galileo used, and it had a lens at one end and another lens at the other end, and that's how you make the telescope. And it turns out you can do that, but the problem is, as you want to make your telescope bigger and bigger, which we always want to do in astronomy, we always want the biggest telescope we possibly can. As you make that lens bigger and bigger, it's getting heavier and heavier, and it's at the far end, it's at the end of the telescope. And so you're top heavy, and any tube that you have to hold this whole thing together is going to sag under its own weight. And so there's a sort of maximum size that's really practical, and the biggest one was the 40-inch refractor at Hipparchus Observatory, which is where George Ellery Hale was before he came here and established Mount Wilson Observatory. In this design, we don't use the primary lens, we use a primary mirror. They do the same thing. I used to call the telescope a light bucket, but a colleague of mine at Las Campanas Observatory, Dave Ossip, really corrected me and says it's more like a light funnel. You're taking a certain amount of light, essentially this much light, it's coming from outer space, and eventually you're bringing it all the way down to something about that big where it comes out. So you're really concentrating the light, and a lens can do that. You probably use magnifying glasses, and you can make the image of the sun if you want to burn some leaves or something. You can make that really concentrated in a small piece of area. This mirror can do the same thing. It's a parabolic mirror, and it takes the light and it converges it and concentrates it. And then we get to the top, and hopefully you can see at the top of the telescope, there is another mirror. That's the secondary mirror. And so by the time the light gets up there, it's about the size of that mirror. And then it reflects back down to the bottom. Now, in some telescopes, there's actually a hole in the primary mirror and the light will come out the bottom. That's a Cassegrain focus. This is not. We have a third mirror, which you can't quite see, although maybe later on when we have a telescope pointed really far over, we can have a look at it. But it is at 45 degrees and it sends the light out here. And at the moment, we have a camera stuck up there because unfortunately, you guys are not allowed to be up here with us. So we're doing this remotely, and we've been doing this for a few months now. And we've been using these electronic cameras to simulate what it would be like for you to be here. And what else can we say about this? Well, yeah, one of the big advantages now is this mirror down here weighs about a ton. So it's not light. We haven't fixed that problem, but it's at the bottom of the telescope. So this is a much more inherently stable configuration for making a bigger and bigger telescope. And the other thing is, because we're using reflections, telescope, if you had the equivalent refracting telescope here, it would have to be 3 times as long as this telescope is. Because in a refracting telescope, you don't get to bounce back and forth along the telescope. You only go from one lens to the other. Here, we reflect once, reflect twice, all the way down. So the light goes once, twice, 3 times down, and then out the exit. So we can make our telescope a little more compact. So even though this telescope is bigger in diameter than the Yerkes Observatory was, or the Yerkes refractor, the dome was a lot smaller because the Yerkes was just so long, it had to fit in this ginormous dome. And the other, one last thing I'll say about working with this kind of telescope versus a refractor is we like to do something that's called spectroscopy. And that is where you take the light and you break it up into its different colors. So just like when you have sunlight go through a prism, it comes out as a rainbow. We like to do that with starlight. We take the light that comes from the star, break it up into its colors, and we can see features in that that tell us about what the thing's made out of, how fast it's traveling towards or away from us, all kinds of interesting things. The problem is, if you use a lens to focus your light, that lens kind of itself is like a prism. And so you might focus the blue light, and now all of a sudden your red light is out of focus. Or you might focus on the red light, but now your blue light is out of focus. And so you can't look at the entire spectrum at once and have the whole thing in focus. Here, we're using a mirror, and you don't have that problem. And so it's really great for doing spectroscopy. Okay, what else? Well, we have something else that people often ask us about are these contraptions here on the side, which look kind of weird. And in particular, this tube right here, it's got a pulley system, which is attached to this kind of thing. And what this does is as the telescope moves, and we'll probably show you this later on when we're going from one object to another, this cable gets pulled or released. That goes over here, and in the tube, there is a weight, and I think you can probably point it down the tube maybe. Oh, but I'll hold that. And if you look down the tube, yeah, you can see it down there. There's a weight on, and it's actually got some little wheels so it can slide up and down this tube. And that just works to keep the telescope in balance as it's changing positions from place to place. Oh, and we should look at the mirror. Just point it over. So the bottom of the telescope is open here. And down here, you can see that there's sort of this green color, maybe. Let's see. Let me try. You hold the light, I'll do this. So there we go. In there, you can see the green. And it actually looks like there's something in that glass, but what you're seeing is a reflection. So this tube here is reflected up there in the mirror. And so the mirror is, I forget, how thick is that?
9 inches.
9 inches? Okay, so it's 9 inches of glass. And then on this top surface, we have a layer of aluminum, and that provides a reflective surface. But it means we can also see the reflection on the underneath. And you can see all these sorts of pads and things, and those are just there to hold the weight of this 1 ton of glass. Okay. There you go. And let's go over here, because we're talking about weight. So the mirror itself is a ton. The entire contraption here, trellis, everything else, is 22 tons. And that's a lot of weight. And it's a lot of weight to put on a bearing. And so what they did was they made this big, sounds empty, but I hope it's not. This big tank here, and inside this tank, you should imagine that we have a float, which is about the same dimensions as the tank. So very little space between the tank and the thing that's actually floating in there. What's it floating on? Well, it's floating on about 600 and so pounds of mercury. So they dump the mercury into here, you put the float in, that displaces the mercury, and thanks to Archimedes' principle, the volume of mercury that you displace is the amount of weight that you are putting down on it. And so to displace 600 pounds of mercury that much, it's about 22 tons. So the weight of the telescope is on this layer of mercury. And it's a liquid, and so it's good and frictionless. And we can float the telescope. And down here, we have a little indicator. Did you give me the flashlight? Or did I think I've got my flashlight somewhere here. There we go. So here we have the level. Can we see it in there?
Yeah.
Yeah. And you can see there's some tape telling us that's probably where it should be. And it looks like it's topped up, which is good. So I didn't bring any spare mercury with me. So, and here's a question for the director. When was the last time this was opened up to put more mercury in?
In the last 20 years, nothing.
Okay. We don't want to do this. Keeping it in there. And in the old days, apparently this was open to the air. It wasn't sealed up. And I guess every now and then you'd come in and find a little mercury on the ground. You'd have to clean it up with a special vacuum of some sort. But now it's just completely encased for obvious reasons, since mercury is toxic, or at least the mercury oxide is toxic. Okay, I think we've pretty much gone through. Do we have any questions that are coming through at this point about the telescope? Okay, you can probably tell, if we look, you can see it's actually kind of gotten a lot darker now. Before we could see very clearly the sky, but now it's good and dark. And so probably what we're going to do is start with some stars because we don't have a moon tonight. Last time we were up here, we had a nice quarter moon, so we could spend some time looking at the moon because it's nice and bright. But tonight we don't have a moon, and that was on purpose so that we can look at what are called deep sky objects, galaxies, things like that. But to look at those, we got to make sure it gets as dark as it possibly can. So for a little bit, we're going to look at things like double stars. I think we've got a triple star system. And this will also allow us to focus the telescope nicely before we move on to the fuzzy things. And it will also give us an idea of what the seeing is tonight, how steady the atmosphere is. If it's really nice and steady, then those double stars will be able to be split very easily. If the seeing's not so good, then they'll just look kind of blobby and they'll all kind of merge together and we won't see very much at all. But I think it's looking pretty good. What do you think? Yeah? Okay. All right. Did we introduce Daryl? Sorry? We're on Zeta Cancri. Okay. By the way, this is Daryl Dooley over here. He is a telescope operator for the evening, so he is the driver. And what he says goes for whether we can go somewhere or not. Okay, so we're good to go. We're good to go.
Right.
So let's go back to the thing, and I will mute this.
Back over to me just for a minute. So what we're going to be looking at is a multiple star system, and this is Zeta Cancri, and it is a binary star in the, well, it's a multiple star system, so there's a binary star component and a triple star component. It is in the constellation of Cancer. If you know anything about the constellation of Cancer, it does look like a faint collection of stars that make the letter W, but it's supposed to be a crab. So you need some really good imagination to see some of the constellations as described by the ancient Greeks and Romans. But I'm going to go straight over to the telescope view to see what we can see. And there it is.
Yeah, I guess we
A
should turn the
very
lights off.
faint.
Okay, so the question
Wait a second, hang on.
is, not seeing
Is
it?
this,
No,
is that the right one? Because,
That's a previous one. We don't
That's
have a
a-
live link
oh, we don't have a live
on
link?
your thing.
Uh-oh.
So that's something where you have to reset it.
Do we have to reset it?
I
Huh.
can have a look and check.
Okay, I'm gonna hand this over to people who know the ins and outs of our system a little better.
Okay, let's see here.
I was about to say, that's not what I'm seeing on the other monitor.
Okay, let's check to see if the dome view is working first. Apparently, nope, it's not working. Okay, so what is going on?
We did have a laptop crash just about 10 minutes before we started, but this was working prior to that.
Properties. Let's try doing this. And then go back.
Yeah, it says
Yep.
Are we back there?
Mm-hmm.
All right,
Yep.
so that's working now. And let's just
Yay.
make sure the dome view is. Yeah, okay, that's good.
All right.
All right. Phew. This is where you have to restart everything.
Oh, that's always a concern. So one of the reasons that we are looking at stars to start with is we want to be able to focus our telescope. So just like if you're using a camera, you want to be able to focus at the object that you're looking at. We want to be able to focus this camera that's attached to this telescope. And it is
I'm gonna zoom in a bit, maybe.
not bad. Yeah.
I think the scroll over just, yeah, there you go. And the question is, can people tell that this is a triple star system?
Yes, it's right there.
Well, I'm not asking
I know what
you.
out of focus blurry looks like.
I'm asking if the folks at home can tell that this is a triple star
When the
system.
blur is twice as wide, that's 2 stars.
Yeah, there you go.
The blur is twice as
When
wide.
it's twice as
Yep.
blurry, it's 2 stars. So the star on the right and the star on the left, those are clearly, obviously separated but the one on the left is two stars close together. Now, this is giving us an idea either of what the seeing is like tonight, or, oh, that's better, and
They're still not coming together.
so as you watch this happening, what's going on is Tom is at the telescope and he is turning this dial, and as he turns the dial, the camera is moved closer and further away from essentially the primary mirror. And so that's what brings us in and out of focus. But of course, he's also fighting what's called the seeing. And so he might get an image that looks good, and then all of a sudden our sky goes a little turbulent and it makes the image a little blurry. And so we kind of have to make a call at some point to say, okay, this is good enough, and we're not going to get any better, at least until the seeing improves tonight. It may very well, because it's still early. The ground is still cooling off, and so we are probably still getting heat waves coming off the sky, off the ground. And we are kind of looking off in the west, so,
There's LA down below.
and there's LA down below, of course. That is never going away.
Yeah. Yeah, LA.
Well, here you are, this is our beautiful, that's what we compete with. About 10 million light bulbs.
No, 20.
20 million light
Oh,
bulbs.
Yeah, so
yeah, I was
everybody
going to say
gets
only
to-
10 million?
20 million lights.
So if those people at home could turn off their lights,
Yeah, if you could all turn off your lights, please.
This is, so this is, from here, LAX is right about there. Orange County's over here. And this is downtown Los Angeles. You can really tell.
Yep. So, all of that light is what astronomers call light pollution, and it is brightening up our sky. So we have kind of fussed with the parameters in the software that controls the camera, and we have darkened the sky as much as possible, or kind of blocked out that sky glow, if you would. And now we can see these objects. So these okay. Just had the laptop screen went blank, and I thought, oh no, not again, it's not rebooting again. I gotta be careful not to touch this laptop. It's having a tough evening. So the distance to this particular star system is around 25 parsecs, which is 82-ish light years. So for those of you who don't know how to measure distances in outer space, there are various units that astronomers use. I mean, certainly here on Earth, you can use inches and feet and miles, or if you like metric, then you can use millimeters and centimeters and meters and kilometers, things like that. Within the solar system, we use the distance from the sun to the Earth as kind of our base unit. That is one astronomical unit. And we can figure out that Neptune is 30 astronomical units away from the sun. So it's actually 30 times the Earth-Sun distance away from the sun. So Neptune's really far out there. AUs are pretty good if you're talking about things within our solar system, comets, planets, dwarf planets, things of that nature. But our solar system is like 100,000 AU across. And if you're going to have really big distances, you like to have other units that you can use where you don't have so many zeros. So a light year is the distance that light travels in 1 year. And you may think, how can you measure a distance using time? But really, we do it all the time. Because my commute, back when I had a commute into work, was, that was a 20-minute commute. And so in traffic, it was a 30-minute commute. But you can kind of gauge your distance knowing the speed at which you travel. Now, a light year is the distance that light travels in a year. Light travels really, really, really fast. And our solar system, which is about 100,000 AU across, is only 1 light year across, approximately. So we have something at 82 light years away, these stars here. As well as light years, there is a different unit that astronomers use called a parsec, and that is objects that, well, it's parallax angle of 1 arcsecond, which I'm not going to get into, but a parsec is also a unit of distance that astronomers use. So we got 82 light years away for these objects, and I'm just going to read from Stellarium here. It says Zeta Cancri is a star system in the constellation of Cancer, containing at least 4 stars. It also has the traditional name of Tegmine or Tegmin or Tegmeni, and I'm not sure if I'm pronouncing those correctly. I'm not sure in which language or from which language those names are taken, or which culture. It is approximately, this says, 83 light years from the Earth and has combined apparent magnitude of plus 4.67, which brings me into magnitude scales. So inevitably, if you look out there, I just looked at the YouTube chat, and Tim is giving all of the conversions. Wow, that is really precise. Holy cow, thanks, Tim.
He was a JPL astronomer. They have to be precise out there. No room for error.
Yeah, so the stars we're looking at have an apparent magnitude of plus 4.67. Now, the apparent magnitude scale was introduced by Hipparchus back in, I want to say Hipparchus is like 150 BCE? I don't know.
I don't know.
More than 2,000 years ago. That's when Hipparchus lived. And Hipparchus was a pretty well-known astronomer in his day. He compiled the first star catalog, and he also devised a way of using the star catalog, figuring out or kind of describing which star is brighter and which star is not so bright. So for Hipparchus, the first magnitude stars, or the first class stars, were the brightest stars. So these are stars that you would easily see in the night sky. Sirius is a first class star, and I think Betelgeuse would be the same, and Arcturus, and Vega, some of the other nice
Sirius.
bright ones. I said Sirius.
Oh, sorry.
And the ones that were bright but not quite as bright were considered second class stars. All right, so Casey, thank you. It's 190 to about 120 BC or BCE, before the Common Era. And yeah, so Hipparchus lived a long time ago. The third class stars, according to Hipparchus's magnitude scale, were the ones that were more dim. So his scale went from 1 to 6, 1 being the brightest stars and 6 being the ones that you can barely perceive during a really dark night, so when there wasn't a moon above the horizon and from a very dark location. Although when Hipparchus did that, there wasn't a whole lot of light pollution. Cities didn't have electric lights, and the cities weren't that big where he was. So plus 4.67 is pretty dim for humans to be able to see. Would we see it from Greater Los Angeles? No, we would not. Not with only using our eyes, or what astronomers call naked eye. With the aid of telescopes or even binoculars, these stars, this collection of stars known as Zeta Cancri, is something that you can see. So binoculars are like 2 little tiny refracting telescopes that you hold up to your eyes. And a refracting telescope uses lenses. The one that we have here is a reflector, which uses mirrors. And the whole idea of using telescopes in the first place is to gather the faint light and funnel it down to our equipment. Now, for those of you who may have a telescope at home, the equipment that you may be using is your eyeball. So you're using a telescope, and then you have an eyepiece, and you're looking through the eyepiece, and all of that light that is gathered is going to your eyeball, and then down into your brain, down your optic nerve. Or you can use a camera, like we're using here on this telescope, to collect the light so that we can see Zeta Cancri.
We can move on to the next object, I think.
Awesome. Okay, so what are we going to next?
We're going to go to another double star in Cancer because it's right close by. And usually we bring the lights up to see the telescope move, but it's not going to move very far, so...
Yeah, if it's within the same
We're not-
constellation.
We're not going to bother. So we can just leave it on the camera, and in a second you'll see those stars zip away, just to show that this actually really is a live view.
So we have Daryl over at the controls of the telescope, and he is going to put in the new coordinates, and we are going to go to a multiple star system called Iota Cancri. So Zeta was the last letter in the Greek alphabet. Iota is
Boy, you know, we had that question last night, and you'd think I'd
neither
I'd
the
look it
first
up.
nor the last.
Oh, here we
So
go.
was it alpha,
Alpha,
beta,
beta.
savons?
Nice.
All right.
Alpha, beta.
Just got to look up the Greek alphabet, but that's how it works. You can explain how it works.
What's the third one? And then it's delta.
Alpha, beta, gamma, delta.
Alpha, beta, gamma, delta.
And
And then other things like iota. So this is a wide binary system, and it is the second brightest star within the constellation of Cancer. Now, it is, without a telescope, it looks like a single star. So this is why they call it a star, but it's actually a star system. And these two components are actually pretty widely separated. They're separated by, about half an arc minute. So we got 30.5 arc seconds. And if you are new to measuring things in the sky, then we have the entire sky kind of horizon to horizon being 180 degrees. As you may remember, there are 360 degrees in a whole circle. And what you see above your head is a hemisphere, or half a circle. And so you got 180 degrees. Each degree itself is divided into minutes of arc. So instead of being divided into like tenths or whatever, it is divided, each degree is divided into 60. And each 1/60th of a degree is called a minute of arc, as in, yes, seconds, minutes, hours, time telling. And these two stars are separated by just about half of an arc minute, which is half of a 60th of a degree. So that's 120th of a degree, which is not something that your eye can perceive without the help of a telescope. So there are a number of reasons astronomers use telescopes to gather the light so you can see the faint objects, but also to resolve the fine details. So you want to be able to see the really fine details. I don't know if you've ever looked using Google Maps at your own home address, but the building that you live in, you can see it from a satellite image, and you can see Google Earth, and then you can zoom in, and you can zoom in, and you can zoom in, and every time you zoom in, it seems to refresh until you get to the limit of the capability of the camera taking the picture. And then you try and zoom in more, and it doesn't refresh and give you a more detailed view. It just seems not out of focus, but it doesn't have a lot of detail, and that is lack of resolution. Wow, these are bright.
Yes, they're bright. They're bright. They're a little over bright.
I was about to say, is this the same exposure rate? Because these are comparable. I mean, the last stars were plus 4.67. This is plus 3.93.
Yeah, but we're at 1/4 the exposure rate. And we can actually pick the blue out of the top one and the yellow out of the bottom.
Okay, so we changed the exposure rate. Clever.
I think Zeta Cancri was also magnitude 6.
It says plus 4.67.
Well, it depends on which component. I mean, there was
possibly,
the companion
yeah.
might have been smaller.
So this is not Zeta Cancri, this is Iota Cancri.
And by the way, Barbara pointed out that it is the 9th letter of the Greek alphabet, and so it is the 9th dimmest, the 9th star in order of brightness in the constellation of Cancer.
So the 9th brightest.
9th brightest.
Yeah. All right. And Zeta is the 6th. Yet Iota is brighter than Zeta. That doesn't make sense. Clearly, whoever was doing this
Well,
messed up.
Was drinking at the time.
A little too much coffee that night. They had the jitters.
All right, so the question is, can we tell the difference in colors here? Because this is one of those doubles where you are supposed to be able to see that one is kind of orangey and the other one is sort of bluish.
Well,
Sorta coming out.
we have two blobs on the screen in front of you. There is a smaller, less bright blob up to the left,
The diffraction is where we see the color.
and then the larger, brighter blob is in the center of the image. And if you kind of look between them, you can sort of see that the larger has more of a golden, warm color, and then the smaller one, every so often where it seems to have, what you generally refer to as if you ever draw a star, the pointy bits of when you're drawing a star, the pointy bits, they seem to have a cooler, bluer look to them. So this is because these two stars actually do have different colors. So we have the primary component, which is Iota Cancri A, is a yellow G 7.5 type bright giant. So this is a star that is cooler than our own sun. Not a whole lot cooler, but a little bit cooler than our own sun, but physically a lot bigger. So this is a star that has evolved off the main sequence to be a giant star. And the companion star, which is Iota Cancri B, is a white class A3 main sequence star. The apparent magnitude of this dimmer star, the one up and to the left, is plus 6.58. So there you go. So it says, I'm just reading from SkySafari here, although the colors of the stars do not differ by much, their contrast caused early observers to declare them, quote, clear blue and pale orange, end quote.
Interesting comment from the Center of Excellence for Dark Matter. Yes, if we were to defocus the star a little bit, it would bring the color out a bit, but I'm afraid the director would kill me if we defocused, because we're going to soon go on to something a little more challenging, and we want to try and maintain
Keep
focus.
it in focus, yeah.
We have a bad habit of getting out of focus and then losing ourselves. Partly because the focuser that we use on this telescope isn't really the greatest thing to use with a CCD or a CMOS camera. It's designed to hold a 6-inch eyepiece, 4-inch eyepiece, and it's just it's a monster, and it's really hard to focus. So I will say yes, defocusing would help, but we're not going to do it.
But I don't know if I'm imagining seeing the warmer golden and then the cooler blue. I don't know, you guys can put it in
go
the
ahead.
chat and see,
We're going to bring the lights up.
tell
You
us
can turn-
if you can see the color.
Yeah, if
All right.
you want to show that. Let's show the telescope. Let's show the telescope move with the lights up.
Okay. So now we have the dome view. I'm over here in my blue jacket, and this is our whole dome. The feed that we have right now is a GoPro with a wide angle lens, and you can see our telescope in all its glory. So I think Daryl's going to move the telescope and possibly move the dome, so it'll get loud and squeaky in here.
But now you can see it go. And now you can see that and you can hear that when this telescope moves, it's very quiet. When we get the racket is when the whole dome starts to rotate around.
Oh, the focuser was built by the LAAS, so I think if we're going to blame anyone.
Oh, okay, we're going to blame them.
No, it's excellent.
No, it's excellent.
Oh, it's excellent.
It's excellent, yes.
It's excellent.
For eyepieces, it's perfect.
For this one?
Okay, actually, what I should say is that for when we have an electronic camera like this on there, what would be really nice, hint, hint, it would be one that's electric, the electronic focuser, so that we could, so Richard has, on his telescope, he has an electronic focuser, which makes sense because he's not there to turn the knob. But you can run this thing through a routine on some of these software packages that will then focus the telescope for you, and you don't have to kind of eyeball it. Yeah, okay, so now Richard's going to bring in a view from his dome. Hold on, let me bring this over to you so they can hear you.
Oh, she's got all the details. Jenny's got everything.
I have all the details?
Oh, okay.
What?
We'll be looking through the refractor, which is in a remote location, and we'll bring up its image. And that's M3. Globular cluster, about 42,000 light years away. Still think I need to do shorter exposures.
Maybe. It looks a little fuzzier than it did before.
Yeah, it's stacking them more and more and more.
Okay. Because I'm seeing donuts. I think I'm seeing donuts.
And there.
That's looking pretty good there. So this is an object we'll be getting to with the 60-inch a little bit later.
Oh, are we?
Oh yeah, we'll do a globular cluster, I think, and that way you'll be able to see the difference that the different optics do. And one thing the 16-inch gives us is a very, very narrow field of view. It's an f16 with a 60-inch diameter, and so that's a huge magnification. And it means we can zoom in on some very interesting things. But when we have people come up and say, hey, can I look at the Andromeda Galaxy? You can look at the very, very inner core of the Andromeda Galaxy. You cannot see the whole thing. And if you look at the moon, you can choose your favorite crater, but you're not going to see the whole thing at once. So it has its advantages and disadvantages.
With this refractor, we can see pretty much the whole globular cluster. And for those of you who may be unaware of what a globular cluster is, it is basically a glob of stars that have clustered together. I mean, I love the name. This particular globular cluster was, or has about 500,000 stars that are gravitationally bound together, and it is moving as a unit through space. And this particular globular cluster is estimated to be around 35,000 light years away. So it is very far away, and globular clusters are usually located above or below the disk of the Milky Way galaxy. And that's what we have here.
Okay.
We're gonna move
go
over
have
to
a look.
60.
And we're going to have to bring up the exposure.
All right, so we are now looking
Well, we'll see.
at M3 with the 60-inch?
No, this is.
Oh, okay.
We're
I was about to
looking
say, we're
at.
not there yet.
Well, you tell us what it is.
Oh, wow. It's a jellyfish.
No.
Kidding.
Are we zoomed in at all on that, or are we zoomed out? I can't remember. Pretty much zoomed out. All right. And now this is where we're going to have a little fun with focusing. Are we
That's
focusing?
pretty focused.
I think we're good? Okay, good. That's why, because we don't like focusing when we don't have to.
Wow, look at that center star.
Especially when the...
That's beautiful.
Is this the ghost?
Bring up, that is the ghost of Jupiter. Which we should
So this is known as the ghost of Jupiter, and it is a planetary nebula. And it has Jupiter in its name, and it's a planetary nebula, but believe it or not, has nothing to do with planets. This is many, many, many thousands of times the size of any individual planet. This is a white dwarf star surrounded by a special type of emission nebula. This is material that had once been part of the star that got expelled into outer space and is expanding away from that white dwarf as a bubble. But it doesn't get expelled in a very smooth, even manner. You can see here there's kind of one bubble inside another bubble. And this is material that can be expelled kind of explosively, and then there's a quieter period, and then the star can do it again. When stars have used up their nuclear fuel and are kind of dying out, sometimes they can do so in quite an impressive manner. Now, this particular planetary nebula, nicknamed the Ghost of Jupiter, is also known as NGC 3242. And I'm having something pointed out to me.
Well, Daryl was looking at the picture and he was wondering if there was, if that was those blobs that we're seeing on the ring are real. And so we were just comparing it to, I guess this is I don't know if this is a Hubble Space Telescope picture we have here, but
NOAO.
it's
yeah.
definitely real.
Yeah. So
Those bright spots are bright.
Yeah.
And so the bright kind of nodules you see in that inner ring, they're real. So this is, evidence that the expulsion of material was not smooth. It kind of globbed together in some areas and, shows some turbulence. This particular nebula was first discovered or first viewed with the telescope in the late 1700s by William Herschel, who was a very well-known observer. He found, inevitably, if it's faint and interesting, it was probably first imaged by William Herschel. He was just, I don't think he ever slept at night. He must have slept every day and then just observed every night all the time, because he discovered a lot of things. This one in particular was discovered the night of February 7th, 1785. Okay. Which is impressive because February in England is not generally good observing weather. So the fact that he was out in February in the UK is pretty impressive. NGC 3242 can easily be observed with amateur telescopes and appears as a 7.7 magnitude blue-green oval, about 16 arc seconds by 26 arc seconds in diameter, plus the larger ring around it. So I had talked about arc minutes. There are 60 arc minutes in every degree, and you can further divide arc minutes into arc seconds. So there's 60 arc seconds in every arc minute, and then 60 arc minutes in every degree of arc. And if you do the math, 60 times 60, 3,600 arc seconds per degree of arc. So if you can imagine dividing, well, if you hold your pinky finger up at arm's length, then what the patch of sky that is basically blocked by the diameter of your pinky finger is 2 degrees of arc. So that's 7,200 arc seconds that you're blocking with your pinky finger. So the fact that we can see with our telescope down to 16 arc seconds is pretty darned impressive.
We were just, if people were wondering why we got double vision there, we were trying to do a technique called stacking. And what you take a live stacking, and you try to take a picture and then you take another picture and you average them together. But the software has to be able to line them up. And if you haven't got a whole lot of stars, which we don't, because the field of view of this is very small, it can get confused. It's trying. It's just rejecting everything we try.
Yeah, it's just rejecting.
Oh well, it was worth a try. Well, let's turn it off and just go back to regular live view. This is actually looking a lot better.
Yeah, it looks beautiful, actually.
It's actually
So
better than the-
this
Yeah.
ghost
Video
of
mode.
Jupiter is difficult to determine the distance to. So there's some estimates that say it's about 1,500 light years away, so 1,500 light years away. Other estimates are saying that it's about 2,500 light years away. If you don't know how big it is in reality, then you don't have an indication of how far away is it. So rather, is it large? Does it have a big diameter and is it farther away? Or is the diameter smaller and it's closer? Both of those things would give us the same view. And it's kind of out there on its own in space, so it's really quite difficult to determine the actual size of this object as well as the distance to this object. But it is a very pretty object.
Yeah, we were up here last night with a small group of students as part of a STEM program, and they were looking at this not with the camera, but with their eyes. And this is only, I would say, a little bit better than it looked with your eye. So using this telescope is really, really quite good at getting objects like this, which are small on the sky and relatively high surface brightness.
It's too small.
It does kind of look like an eyeball,
Yes, it does.
cat eye.
I
It's
guess-
not the Cat Eye Nebula.
It
There
is-
is
no.
there is another similar planetary nebula called the Cat Eye Nebula, which
That's gorgeous.
totally looks like the eye of a cat, and the slit pupil, but this is not that one. All right.
Yeah,
So we've-
in the refractor, it's a joke.
Well, let's
Do you
bring
want
it
to
on
pull
over.
the refractor?
Bring it over and let's have a
So
look.
we are using this evening both the 60-inch telescope, the view of which you are looking at right now, and a 5-inch refractor.
5-inch refractor, this is magnified at 200%, and it's still a little tiny thing. It
Yeah.
just goes to show you how much the 60-inch can reach out there and grab a small area
And
of
just-
space and really show you what's going on.
Yeah.
And what's the exposure on this one right now?
This one right here is at 6.5 seconds.
6.5 seconds. Okay, so the exposures are comparable.
Yeah,
Yeah,
but note the detail is,
yeah.
and if you go to full size, it's that little tiny blue dot right there. So, not quite the same.
Yeah.
So
Likewise, there are objects that we simply can't look at with the 60-inch because they're just too big. So we'll often have people come in and ask for things like the Horsehead Nebula or whatever, and they're just too big. But on in a smaller telescope like Richard's, it would be great because you have a nice wide field of view. Got any questions going on there?
Yeah, so there was one question from Sierra Ludo. Can you see any binary star systems like Tatooine? Because May the 4th be with you, people.
Of course.
Oh,
Absolutely.
right. How do we forget that?
So
It's right next to the Mobari Nebula from Star Trek, which doesn't exist either.
now you're mixing science fiction universes,
Yes.
Richard.
359 is a
There were some binary stars that we saw at the beginning of the live feed this evening, and we may go see another binary system, but those are the binary stars we're looking at. We're not actually looking at planets orbiting the binary stars. To my knowledge, there's only been one planetary system that's been directly imaged.
I think there might be more than. I mean, this,
Is there more now?
Well, Fomalhaut was like the first, I think, but I think they have another one. But I'm not a
Yeah.
planet person.
So, yeah, we're not planet people, so we're not necessarily up with the latest and greatest. Certainly, there are more than 5,000 planets orbiting other stars in our galaxy that we well, the royal we, that have been discovered, but their discovery was not by direct observation. It wasn't, we took pictures of these planets and we could tell that they were there. There are different techniques that were used to determine that there was a mass that accompanied the star. So there's Trappist, one of the Trappist 5?
Oh, that, you mean the one with the multiple planets?
Yeah, but wasn't Trappist 5 a binary star?
There is a binary. There is a
I
binary,
do know
yeah.
there is a binary star system around which planet or planets are orbiting. And that has been dubbed the Tatooine system. I don't know what the real name is.
Well, let me look it up.
And, well, we have multiple devices here to look them up. Tim has chimed in on the chat, more than one, I think, but not many, to be sure. So there are many, many, many binary star systems. In fact, more stars are part of binary or triple or quadruple systems than are single stars, like our own sun. So
I looked that up one time and it said, yeah, 51%, which I really kind of thought was cheating.
51%?
I said, well, that's kind of cheating.
50 plus a bit. But yeah, so are we special? I guess we're in the minority. Does that make us special?
No.
No. Okay.
Not at those.
Not at those numbers?
Not a slight percentage, no.
I like to think we're special. I mean, we're here, right? We're looking up at the sky. How many other intelligent life forms are doing some stargazing tonight?
Then we're all special.
Okay.
Well, no, I mean
so
the other species, like dolphins. I don't know how often they stargaze.
exoplanets.nasa.gov.
Okay,
think it is-
exoplanet.nasa.gov. I'll put that in the chat.
Yeah, it's got Trappist 1E as the.
So Trappist has 2 P's, right?
Yep.
So Trappist 1E, which I just put into the chat,
I'm
is
guessing Trappist 1 is the star system and E is the A, B, C, D, 5th planet that they discovered, and I'm guessing it's the one they think could be habitable.
yeah.
And that's why it's a Tatooine-like planet. All right, I'm going to go find out where we're going next.
Where we're going next, after the Ghost of Jupiter,
After the Ghost of Jupiter.
find out what our target is.
This is not the Sombrero. I was hoping you guys would do that and we would use this one.
Oh, that's the one you're talking
4565.
Well, I think the telescope operator and the executive director and our friendly neighborhood astrophysicist are over there deciding what our next target is going to be. It is kind of like watching kids
So we'll do Sombrero.
at,
That's perfect.
opening
Comparison,
presents.
Yeah, if I can get it
All of them over there looking at what target we're going to get to next.
So we're going to go for the Sombrero galaxy. Now, this one's going to be so, and the reason that we're hopeful tonight is that last night we were looking at the Sombrero and it wasn't looking exceptionally great, and part of that is because we're looking way down in the south towards Los Angeles.
Oh, great.
But we're also looking way down in the south towards Los Angeles for this last object we were looking at. So I'm hoping it'll look not too bad.
Yeah. So,
Okay,
oh, and now the dome turns.
here we go. Squeal. Let's
Well, it
walk.
doesn't squeal so bad in one direction. The other direction is much worse.
Yeah, it's twice as big as our field of view.
So the Sombrero galaxy is a galaxy far, far away outside of our own Milky Way,
Yes, I am.
and it is seen among the stars of the constellation of Virgo. So you guys may have heard of constellations, and many people think that constellations are the patterns that the brighter stars make in the sky. Virgo is I think originally Roman constellation,
This guy gets brighter.
Greek, not sure. when you're studying astrophysics, they don't teach you Greco-Roman mythology. I've learned all this more recently. So Virgo was the Virgin, and apparently you can, if you have enough imagination, see a lovely young maiden holding wheat lying in the sky. Personally, I don't see that. And I'm not sure I have any Greek or Roman ancestry. So there are many different sky cultures that envision different things in among the stars that you can see in the night sky. So if you can't see Virgo, don't worry about it. If you see, you know, a laptop or an iPhone up there in the sky, what you're looking at is just as valid as what our ancestors looked at. Obviously, they could never see a laptop because they didn't exist back then. But Virgo has within its boundaries the Sombrero galaxy, which is also known as the Messier 104 object and NGC 4594. So what do we know about the Sombrero galaxy? It is 31.1 million light years from our own galaxy within the local supercluster. About 15 kiloparsecs, or 49,000 light years across, which makes it smaller than the Milky Way. So the Milky Way is about 100,000 light years across. It's got a bright nucleus and an unusually large central bulge. But what makes it really, I guess, iconic in all of the galaxies that have been imaged is that there's a very dark lane, and it is a dust lane. So it's almost...
Here it comes.
Oh, here it comes.
Yeah.
Got it.
So we'll have to play around with the exposure. That is the unusually bright central bulge. And you can think of well, I like to think of spiral galaxies as fried eggs. So if you have two fried eggs kind of back to back, and the yolk in the center has not been popped, then that yolk, which, if you have two fried eggs back to back, kind of makes a ball, that you can kind of think of as the central bulge. And then the disk of the galaxy would be that white of the fried egg. And imagine if you had a lot of dust between those two fried eggs that you've trying to put back to back. In astronomy, what dust does in outer space is it simply blocks the light of the stars that are behind it. So it blocks our view of the bright stars. So it looks like there is, you know, someone who's taken an eraser and rubbed out the light, but the stars are still there. We just can't see them because the light has been blocked. Now, the dust in outer space is not quite the same as the dust that you're going to find under your bed. So dust in outer space is really quite small. And the molecules themselves are much, much smaller than the kind of clumps of dust bunny you would find under your own bed. They're, you know, I don't know, a few hundred atoms combined together. They're microscopic in size, approximately the size of a piece of smoke. So you may not realize that smoke is actually solid, but the tiny, tiny particle, ooh, that's bright, has just been lifted with the heat of the fire. But in outer space, it's not hot, it's very cold. So these tiny pieces of dust are usually encased in ice. There are different types of ices in the universe. We have water ice, we have methane ice, we have ammonia ice, all sorts of cool stuff going on. And you are, well, I'm beginning to see that dust lane.
Well, we're just playing with the settings to try and get enough light but not blow it out with too much noise. So, you know. Oh, gotta fix. And every time we change the gain, of course, the software we're using is completely manual when it comes to choosing what constitutes the bright background and what constitutes the dark. So we have to adjust this every time, which is a little annoying.
Yeah, there's no auto.
No auto scaling. So now we're definitely seeing the dust lane.
Yeah, so there's the bright
There it is.
nucleus, but beneath it, kind of horizontal in the image, is that darker dust lane.
Okay, so we could try increasing the
Last time we did
exposure.
this, though, this thing was really huge.
Yeah,
Huge.
we are dealing with bright background, and it wasn't a
Welcome, LA.
well. All the other thing is, I think we have some high cirrus, which is adding to the background reflected light. So not the best we've ever had, but certainly not the worst. Shall we try bringing it up to 15 seconds?
I think that'll do
I'm getting 4x4.
Is that an airplane or?
That is an airplane.
Oh, okay. It just sounds weird echoing in the dome. A little bit. It's just like, is that an airplane? I don't know if you can hear that out where you guys are, if the sound picked up. But whoa.
Okay. Oh, again, we just have to
Yep.
to adjust the the light levels. Keep it tweaking.
it. Somewhere in there.
Yeah, but
Yes. Contrast is pretty bad down here, so it's going to be hard to get out.
we're looking over the.
Look at you, good.
Yeah, well, there we are. That's as good as it's probably going to get. We could try bringing
Yeah.
exposure up even more, but now we're going to start fighting the. Although it's not looking too bad. Last night we were putting the exposure up, and we could start seeing thermal noise from the chip, but I don't quite see that yet. So we could probably go a little higher. Whoa, 35 seconds. Look out.
Oh, wait a second.
We're going way up. Yep.
So, the Spitzer Space Telescope astronomers found that the dust ring around the Sombrero galaxy is larger and more massive than previously thought, indicative that this is a giant elliptical galaxy, except clearly not very giant since it's smaller than the Milky Way.
Well, it's all relative.
Yeah, I was about to say, we're going to have to do some more research on this.
All right, let's see how this looks. Let me get it.
Ooh.
Hey, this is looking pretty good.
Yeah, that is a very bright central bulge. Wow.
Yeah, but we're not.
And that is a very dark dust lane. This is an interesting galaxy.
You're saying a dust line, huh?
Yeah.
Oh, I guess right here. Yeah.
Yeah.
It's really kind of
It's not as well
a
resolved
lot
as you
of
might want it to
avertive
be.
imagination.
No, you can definitely see there's a dark band
We do have
horizontal
one
in
to
this
compare
image.
with, though.
Yes, so this is all
Yes.
built up. So Richard has another galaxy which we cannot look at with this telescope because, again, it's just too big on the sky. So you can bring that on over. And so this is a spiral. What's the
NGC 4565, and its apparent size is double M104.
M104? Okay, so this is twice
because
as big.
it's less than half the distance.
Okay, so these galaxies are probably comparable in size physically. It's just that one is twice as close and therefore is going to be twice as big on the sky.
And you can see the dust lane.
And yes, here is definitely no imagination needed to see that there is a dust lane through that. And so anyone who's been out to a dark site and you've seen the Milky Way go across the sky, you may have seen that there seem to be gaps in the Milky Way. And that's not that there aren't any stars there, it's just that that is being blocked by these particles in outer space that we colloquially call dust, and it absorbs visible light preferentially, and that's why you see these dark lanes. In fact, in the southern hemisphere, if you see the Milky Way in the southern hemisphere, those dark lanes are extremely prominent, and some of the cultures down there along with the regular constellations stories that they also have stories about the shapes that they see as the dark parts of the Milky Way. There's quite a prominent one that looks like an emu. Looks like yep. So there it is. Now, you're stacking on this one?
Yes, we have 18 45-second exposures.
Okay, so every shot that Richard is taking with this is 45 seconds, and then, sorry, how many did you stack?
18 so far.
18 so far. So each time it figures out how to shift and then average them out. And what happens is, well, you guys didn't see it, but when he had his first image there, it was looking none too pretty because the background was very noisy. But because that background is just random, fluctuations in the pixels, then as you add them up and add them up and add them up, those random ones sort of average out to some smooth gray background, but the stars and the galaxies and everything else start to add up and add up and add up, and you see better.
Kind of clip it out just a wee bit.
And we get it a little darker.
Yeah, because we're kind of getting rid of the gray, the overall gray in the background.
That's beautiful.
Now, if we were able to take the time to do what's called a sky background subtraction, that would look absolutely fabulous. But we're doing this live, so we're not going to go and start booting up IRAF or Photoshop or any of those things and start those kinds of manipulations.
That's advanced.
That's advanced stuff.
Okay.
We should also point out
You
that
want to go back?
it's up to you.
I can go back.
Okay.
I heard a big sigh when I moved it.
I was about to say, this is so pretty, and it's just, the other one did not have the
oomph.
detail.
Yeah, well, that's the way it is. That's the way it goes.
But it happens when you're over double the size, apparent size.
Yeah. It's a lot easier to see.
So another thing I thought we should point out is to do these kinds of live images, we're using what's called a CMOS camera rather than a CCD. And the CMOSs have the advantage of having a very fast readout compared to a CCD camera. And so you can almost use them like a video camera. You can get really, really fast frame rates. Not in this case because we're going really deep and we're taking long exposures, but when we were looking at those double stars, you were seeing it almost kind of, a frame a second-ish sort of thing?
Faster than the camera can.
Well, fast, yeah,
It's
yeah.
26 megapixels, and it can only do 3.5 frames a second.
Yeah, and a lot of that has to do with how fast we can transfer the information from the camera to the PC through a USB 3 cable.
So we have details on the emu figure.
Oh, cool.
It starts at the coal sack in the Southern Cross and stretches out through to the dust clouds in Sagittarius, at least. So
It's
there you
huge.
go.
It's absolutely huge.
Yeah. Oh, yeah. It stretches not halfway across the sky, quarter of the way, maybe a fifth.
I've never seen it firsthand, so I couldn't tell you.
Oh, I think I've seen pictures of it. Well, we've seen it in the planetarium.
Oh, right
The
here.
advantage of working in a planetarium is that we can go to other places. We can look at the sky as observable from Australia or South Africa or Brazil or the Antarctic.
We're going to blame this on Elon Musk, but we got a satellite that just zipped right through the
Did
moon.
it? Oh, I missed it.
No, it's there, it's on the.
It's on, and here we can still see the line.
Can you see it there?
No,
you can't see it on YouTube. I think it's a little too.
Too faint.
The compression got rid of it.
Wow. No, I can see it. It's just above and to the right of the galaxy, isn't it? At a little bit more greater
Tilt. Yeah.
distance at the bottom. Wow. Yeah. But okay. Yeah. Anyway, I was bragging about the planetarium I usually get to teach in. Well, not lately.
Yes.
I haven't turned the planetarium on in a long time. I should get back to that.
Yeah, good
miss the
times will be
dome.
coming soon.
Yes. If the numbers get better and people get vaccinated, then we may be back on campus and more to what we would consider regular life.
We hope.
We hope. Well, we didn't fully appreciate, I think, what we had when we had it. Yeah, it'd be nice to get back in the classroom, I have to say. I miss seeing my students.
So we're going to move on to another galaxy now.
Ooh. Which one are we going to?
M51.
M51.
Yes, I am.
Okay, Richard, that's not fair. Yours is faster.
The advantage of full robotic control, yes.
If you Google M51, the first hit is the Michigan Highway, just so you know.
Ah, there is also a sort of, I don't know how you would, what genre of music you would call them, but M82 is a group.
B-52s?
Not the B, or wait, is it M82 or M83? I forget. I have their album. I should know this. Nuts. Maybe it's M83. Anyway, they did name themselves after the Messier object.
Good for them. Gotta love the nerdy
Is there a way to
musicians out
clear
there.
out the other one?
Yeah, it's
Sorry?
M83.
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 I found that I could not clear it out of the attic.
Oh, okay.
How do you
So
do that?
M51, for those of you who may not know,
You
is the
stop and then
Whirlpool
you're stuck with
Galaxy.
whatever it is.
And I think you may know from the
I
name
tried to do that one time.
that it looks a bit like a whirlpool. So instead of seeing kind of it edge on, we're going to be seeing it face on. So we get the full lovely swirl of the
Are you stuck?
Whirlpool Galaxy.
We're off that.
Oh, we're off that.
Yeah.
We're there?
Okay.
Okay.
5 seconds. We'll put it on medium. Okay, now we're clear. Now we're good.
Okay.
The Center for Excellence in Dark Matters, like M83.
It is, yeah, it's M83.
I didn't check the chat, but they may very well have got that before you did. Well done. Well done, YouTube visitors. Ooh, you guys.
So, all right, Center for Dark Matter. How would you classify their genre of music? It's closest thing I can come to is they're very much like the Alan Parsons Project, that kind of vibe. So what would you call that kind of music? It's not-
80s?
Well, it's definitely not 80s.
It's not hard rock, it's not folk, it's not pop. I don't know what fusion.
Maybe
It's fusion.
The moment that we get
progressive.
Progressive.
fusion.
Alternative.
Progressive alternative fusion. There you go. Okay, we should be getting. So we're looking. Where are we looking? Okay, so we're looking more towards the east.
The southeast, yeah.
And a little higher
Well,
up.
the telescope's still moving.
Oh,
which is
you're
why
right.
I can't see anything. The telescope, this 60-inch telescope, alternative, says Barbara. The 60-inch telescope is so quiet when it moves.
Yes. In RA,
Yeah,
east to west.
It's a little noisier in the north-south direction.
Do we have anything?
Oh,
Whoa!
Something just went by. That was.
Oh, that's an aircraft. Holy mackerel! That was bright.
Okay, we've got a star. Any stars in there close by?
That must have been. Was that a star that?
Well,
that we
it
just
was.
Slew past.
It could, if we were slewing, it could have been a star that went past that was really bright, or it actually could have been an aircraft that went
Because
through.
that was bright. Like this is a star. Oh, not anymore.
It was a star.
The telescope's still moving.
Oh, I see
Now
it.
you see it. Now you don't.
Fuzzy, there's a fuzzy
There's a
thing.
fuzziness on the left-hand side. Oh, now it's gone.
Oh. Oh.
You see something?
this isn't M80. This
you
isn't M51.
Are you on M3?
I guess we're on M3. M53. Ah, okay. M53. I thought we were going to.
Oh, it's not M51. It's M53.
M50. We're off by 2. All right, let's see who can figure out what this is. Should be be pretty obvious.
Did you shorten that exposure to 5 seconds?
It is 5 seconds.
2 seconds?
2.5?
2.5?
Medium gain, 3 seconds. Kind of steers. We're scooting
So
off.
M53 is not a galaxy.
Oh, I'm sorry.
It is a globular cluster. And this particular globular cluster is in Coma Berenices, that constellation, and it has a mass of approximately 800,000 times the mass of the sun.
Probably good for that direction.
So 800,000 stars, roughly. Some stars will be less massive than the sun. Some will be more massive than the sun. It's a metal poor cluster, which means it has very old stars in it, stars that have been around for a long time, that formed before the universe had a lot of what astronomers call metals, which are elements heavier than hydrogen or helium. So astronomers have an unusual definition for what a metal is, but it's lithium and heavier, so anything with kind of 3 protons in the nucleus and more massive than that.
All right, now the fun.
As elements are fused in the core of stars, and then those stars evolve and die out, and their material gets recycled in space and into new star formation regions, those heavier elements can be incorporated into younger generations of stars. So it's only the very oldest generation of stars that don't have these metals. And by looking at the signature of metals in the spectra of stars, you can figure out how old the stars are. So this is a collection of very old stars that are metal poor, and they estimate the stars of this globular cluster are almost 13 billion years old. Compare that to the sun at 4.65 billion years old. So 3 times the age.
It's getting good. So I think this is one of those cases where we can actually try the live stacking, because we've got lots of stars.
So we do have lots of stars in there.
Yeah, we'll get it.
We are looking at the central region, presumably.
Yes,
We're not
and-
getting all of them.
Right now, we're mostly, I think we're mostly seeing the red giants. So these are all the stars that are just old enough that they've run out of fuel in the center, run out of hydrogen, and are now starting to burn helium and get all big and puffy and red. And we can use that to figure out how old the cluster is, because if we look at...
So there was a comment that the audio is fading, but I'm looking at our audio feed here. It seems to be good. The microphone's still turned on. I can bring it up a little bit, maybe. We haven't done anything to the audio. It shouldn't be fading. Maybe I was facing away from the microphone a little,
Use low gain.
but I will face the microphone now.
Low gain will give you less noise, and then and less stars.
Stars. Oh, where'd the cluster go?
You just got to bring down the levels.
Oh, okay.
It's just the levels that are messed you up. Of course, now they're
Yeah,
chasing.
we will wait a
So,
second for it to come
You know, I'm
back
trying to
us.
think of comparisons to help people understand what a narrow field of view this 60-inch telescope has.
It's like looking through a straw.
Well, I was just thinking that, but if you think of, if you have like a tube, like a mailing tube, something you'd get in the mail if it's in a tube, or, you know, you can get tubes like a coffee canister, and you buy your coffee or your hot chocolate or your Quaker oats. If you have a big tube and you're looking at the sky, then obviously you're not going to see all of the sky. You're going to see whatever's in the tube.
should go into
And
the
this 60-inch telescope is looking down
I think it actually has a better.
a straw, but I'm just trying to think of a super skinny straw. Like a WD-40?
Cocktail straw.
Well, no, like the
Yes, there
WD-40,
you are.
what are they, the tubes for putting lubricant on bicycle chains or something, like that kind of. So if you imagine holding that super skinny tube up to your eye, how much of the sky could you see through that versus, you know, if you cut the end off a coffee canister and you're looking at that? Both would restrict what you could see with, you know, compared to just turning your head around and looking. But, yeah.
Oh, it is stacking.
All right, so people are saying
Anytime
that the
this
sound is
happens,
better
that one,
now.
I meant that
Good to
one.
know.
This one?
That
Juice box straw. Casey,
Well,
yes.
I think
But
Tom has given up
skinnier.
on focusing, so might as
A
well.
narrower diameter. So, but actually a juice box straw is not bad.
All right, so we're trying to stack.
Or like a hypodermic needle, super skinny, something like that.
Not stack.
It's not stacking for us.
Well, it's lost. Oh no, we got two. Okay.
confused.
Well, that's confused. That's not good.
It's confused.
Oh, our poor camera.
It's the software. Camera's fine. So,
Well, yeah, the camera is fine. What am I talking about? It is the software. Clearly, you guys need to write your own software for this particular hardware. So Chris, in his day job, does a lot of coding.
Too much coding.
So, yeah. Many astronomers, that's what they actually spend a lot of their time doing.
you just pull it up on the 5 inch and see the
And writing telescope
I'm not
proposals.
on whatever you're on.
M53, if you want to. He's having too much fun with M51.
All right, so M53, what have we got for M53? It is a globular cluster of around 800,000 stars that are very old, and it is around 60,000 light years from the galactic center.
It'd be too tiny.
It is above or below, depending on which way you're looking at it. It is not in the plane of the galaxy. It is above or below. It's 3 dimensions, so flip it around, look at it from a different area, below or above. And the stars that we're seeing are
And then turn it off.
a little bit orangey, warmish.
Yes.
Learning out of.
If you're on camera there, that's getting a gear period.
Should be. Okay. Let's bring this to. Oops. That's right.
Ooh, playing around with the zoom.
I'm playing around with it. It's looking very grainy for some reason.
Yes. Well, even here, this has been grainy more than normal.
Was that the seeing then?
LA part.
I think it's part of the LA lights.
You got it.
Yeah.
Seeing is actually not bad. We're not seeing the stars bounce.
Yeah, that's what I was thinking. I mean, the sky is pretty steady,
But
but yeah. What we need to get is a lovely marine layer,
yes,
which is also known as an inversion layer. It's when the clouds are low to the city, low to the ground.
called June gloom is awesome.
June gloom. Yes, but it's only May.
I know. We got to get to June.
We got to get to June, then we get June gloom. But what that inversion layer does, the clouds are very low-lying. Here on Mount Wilson, we're at 5,000 odd feet.
5,700, yeah.
5,700 feet. So we are above that cloud layer. And that cloud blankets the city and it keeps the light down. So we have a lovely dark sky when there is that inversion layer. But we don't have it tonight. Tonight we have sky glow because of the city. And there's mumbling over there.
Yes.
Noticing
One of us is kicking us because we forgot a camera at home.
Yeah, we're using an older camera.
Oh, this is the attic.
The attic, yes.
Oh, so I need to go
My
in here and
cat knocked
actually
the box
change
off.
what it's
That
saying.
was that.
So this is not the,
Well, the ZWO is on the refractor.
yeah, okay, so the ZWO, ZWO, we got Australians here, they know what I'm talking
Yes.
about. ZWO is on the refractor. May gray. Oh, that's what they're all saying.
No. Yeah, June gloom is all that offshore clouds come in right up to the
Yeah.
mountain and blanket everything. And
It's lovely.
yes,
And it keeps it nice and cool, at least in the morning down in the city.
yes, and I live closer to the beach, so it unfortunately sometimes it keeps it cold.
A little too cold. Yeah. Yeah. And mosquito proboscis for the tube that you're looking through
Uh-huh.
with this as
A
comparison.
mosquito.
Proboscis.
We can get more than one star. That sounds,
Look, we've got at least 100 there
yes.
in M53.
But yeah, that was the understanding of the time, and that is they didn't realize how big the universe was. I think they estimated 72,000 light years.
Oh, really?
So they want something high resolution to
Yeah.
see what they're thinking, not realizing they missed it by a factor of
Many
thousands. Yes.
Yeah, the universe is much bigger than they anticipated when they built this telescope.
Yes.
And even when they built the 100-inch, they didn't realize how big
The
it was.
100-inch mirror, and this Tim can chime in, was actually built along the same lines as the 60. In fact, the mirror was already cast
Yep.
before this was finished, so that they could move instruments from one telescope to the other. And because instrumentation
sense.
is pretty expensive.
Expensive, yeah.
I think Rosalie would say something about that at Carnegie.
Yeah.
YouTube feed that does here.
Yeah, it's always, you want it brighter here.
Yeah. Let's try that.
Also keep in mind.
That's a bit better. Okay, I think it's
M3
looking
is very
better.
close.
What's that?
Keep in mind M3 is very close.
Yes, we could also compare this with M3 directly. How are we doing for time?
We have...
Half an hour left,
We've got
okay.
about half an hour left, yeah. So how many
'Cause
more...
I did say on Facebook we'd be going to a black hole.
Oh, okay.
that
Well
one.
then,
Eventually, we'll get there.
What is
we'll get there. We're going to hold the black hole till the end, really blow everyone away, so to speak. Nobody ever guessed the size of anything nearly big enough. Yeah. Way back when. Back in the day.
Well, you want to move it on to M3? And then we'll just...
M3.
M3?
Yep, another globular cluster.
There, and then I will... So it's pretty close, right? Yeah. And while they're moving, we'll point out that on the side, on the excuse me, on the right-hand side, you're kind of seeing a bit of a haze
Yeah.
in sort of two locations, and that's, I think, is the thermal noise from the chip. And we started out at minus 20 degrees, so you can cool the chip, but it's been kind of creeping up. Now it's at minus 18.6, so maybe our cooler is not very efficient when it's been on for a long time. That could be. All kinds of different
I'm not
sources
even gonna say anything about that.
of noise.
Don't know. It is
Yes, that's
beyond
called,
my area of
this is called,
expertise.
amp glow.
Amp glow, yeah. That's
Amp
those are-
Glow.
glow.
yeah. We have,
So the newer CMOS cameras have, such as the one that's on the refractor, no, not the one I had, have figured out how to stop that.
Oh, nice.
So, so that when you start taking longer exposures, you don't start seeing that glow on
Glow
one
on the
side
side.
that you have to subtract in post-processing.
Oh, there's always post-processing.
Yes. They make pretty pictures, is what you do.
Oh, wow. wow, the mirror for the 100-inch arrived in Pasadena on the same day that the 60-inch mirror was being installed where we are.
Nice.
That's impressive.
Yeah, that's George Hale for you.
Yeah, George Ellery Hale was just a telescope whiz kid. Well, amazing telescope designer, builder. Fundraiser, therefore.
He liked to build.
Yeah, and he built really good stuff. So Tim is asking 3C273.
Maybe. How badly do you want to see that? We're there? Okay. Yeah, we might give that a try because that's just a different kind of size black hole.
I thought you were going to do that one.
We can certainly do that.
That one is, oh, it's tiny.
Oh yeah.
You're not doing it with mine. Yeah, that won't do it.
We have
It'll make
our
3 pixels.
What's that?
You can start.
Okay. Let's see what we got. So the image you see now should soon be replaced by the new globular cluster, which, oh, there we go.
Much better already.
Bingo!
Yay.
We've got it centered.
Wow.
Nicely done.
That's impressive. Yep, bingo.
Although we're kind of, are you going to try attempting focus or?
No.
No, okay.
Will you give it a shot?
Well, we're stacking at the moment.
No, we're not. Are we? Oh, we are
We
stacking.
are stacking, yeah. So,
That's why I'm not touching it.
Take what off?
So, Charles Messier originally mistook this globular cluster for a nebula. And then he got better resolution.
It's faint fuzzy.
Yeah.
Yep.
I forget how small the telescope was that he was using.
Not large. Because he was in the early, no, he was in the mid 1700s.
Yeah.
Any telescope in the mid 1700s.
Too long to refresh.
Yeah.
Well, I can put the gain up at high and then reduce the total.
I can try.
I mean, think about Newton's
Oh, we can move
reflector was
to
like
medium.
3-inch in diameter, I think.
We could subframe on this, it would be a lot easier.
Well,
Tim really wants you to go there now.
Okay, we'll just look at this real quick
He
and then.
couldn't go there last night, so he wants to go there.
he wants to go to 3C273.
C
3C273.
273.
You are. You know what?
3C273.
It's not a focus issue.
No?
Those are goals. That's coma. That's a result of that focal reducer.
All right.
Mm.
See 'em?
I guess.
Right there's one. There's one. There's one. You can start to see how they look like.
All right. Well. Oh, hold on. Let's make it brighter. Once again,
Oh,
the YouTube looks different. So let me.
you want to go that way?
Oh, you're right. This way.
Keep
That look
going.
better?
Keep going. Keep going.
Really?
Right there.
Wow. Okay.
Yeah, it looks blown out over here for us.
Yeah.
All right. Fair enough. Okay. All right. Well, then, if he really wants to go, we'll go to
3C273.
Okay.
You're gonna do that one.
Let's give it a go.
Do you want to bring? Since we're not gonna go to that one, do you want to bring that one over?
Sure?
Okay. So while the 60-inch telescope is moving,
Yep.
this is what we've been doing with the refractor.
And this is the Whirlpool Galaxy. And its companion. That is beautiful. So,
What is?
3C273.
M51.
So this is off the handle of the Big Dipper.
Ursa Majoris. Yeah, so this is in the north.
Yes.
This is beautiful. Every time I see this, it's just,
So when we teach little kids here, it's from an old 1960s cartoon where the North Star is the handle of the Little Dipper, and it pours its milk into the Big Dipper, and the arc of the handle points to Arcturus, which was the bottom of the flag, the bottom of the kite. That is actually Booties, but it looks like a kite in the cartoon.
oh,
It was
okay.
a kid's cartoon.
I do not remember that cartoon.
It's old.
I was about to say it might be before my time. I've never even heard
It was
of that.
black and white.
Oh, it is old.
Yes, it is.
Oh,
It's
my.
older than I am. So
So, yeah, to me, Booties or Booties or however you
Yeah.
pronounce it, always looks like an ice cream cone with legs.
okay. To me, it looks like an old-fashioned kite.
Yeah, it could. There's something else that I think looks like a kite, but there's
It is kind of.
there's
It may have been hit once or twice.
there's what is it that looks like the bowl and the ice cream can fall off into the bowl?
I don't know.
Corona Borealis? I think it is the Northern Crown, but it doesn't look like a crown to me. It looks like a bowl that the ice cream scoop on the
The
top
only
of
other-
Boetes would fall off into.
The only one that I don't know the younger generation would ever know what a steam pot is, but Sagittarius looks like a steam kettle. It's just what it looks like.
Yeah?
So I'm going to
Teapot?
turn the lights up.
Oh, the lights are coming
Okay,
up.
We're going back over to the 60.
All right.
Are we?
There we go. Inside the dome again. Woo!
We're coming out.
Ooh,
of
that's
here.
bright light. You've been sitting in the dark for a while. It looks very bright. Where are we going?
3C273. We're going to make Tim happy.
3C273.
Ways up.
Yep.
So this is probably the farthest object that we can look at with this telescope.
Tim is a font of knowledge. 7.5-inch Gregorian telescope. That's what Messier's telescope was. I would not have thought it was that
Long
big.
Focal length. That's a long focal length.
Yeah.
Gregorians are like F30 longer.
Wow. Wow. Just remind me of, gosh, what Lord. It was the Irish guy, Lord Hook, Lord.
The Irish guy.
That had the really, really, really long telescope that I don't think they ever used to look through. I'm blanking on his name. He was
The-
Lord somebody.
Something Leviathan?
I can't
Oh,
remember.
is it the Leviathan
Tim,
of Parsonstown?
Leviathan?
Yeah, Tim knows about that one. He talks
Yeah.
about it in his
Yeah.
history.
It was huge, but because of its limited movement
Yeah. Couldn't
and
see.
what they used for a mirror. Yeah, Tim
Tim
does
will
that
chime
all on
in.
the history of telescopes. If you ever become a session director or a tour guide docent, you have to take his class.
All right.
So we should probably set people's expectations appropriately.
You're not going to see very much. Don't raise your expectations too high. And now the dome's turning.
This is more about using your imagination to understand what this is.
Leviathan of Parsons. Yes, Lord Ross.
Is it Lord Ross?
Lord Ross, yeah. So
only
it was
one I
a
knew of, so.
72-inch Newtonian. Newtonian? I thought it was a refractor.
No.
But it's not. The mirror is not glass. I believe it's metal.
Speculum.
I don't know if it was even speculum back then.
See what's
I don't know.
gonna happen.
All right, let's go back to the telescope view. Ooh, maybe not. There we go. Thank you.
Yes, it was a little bright.
A little bright, but I was about to say, looking at us in the dome with our lights lit up or faces lit up by the laptop screens, less exciting. All right, so yes, as Tim says, this is a fuzzy spot that's 2.4 billion light years away. So this is going to be by far the most distant object
Or wishful thinking.
you will likely ever have seen in your life.
Tell Tim I have his chair and it's very comfortable.
Tim,
Okay,
Tom
there's
has your
something added.
chair. It's very comfortable, and the crow flies at midnight.
We had something, they moved it.
Just centering it up.
Oh, I can't, I wonder if I can do it.
So what's that?
So as we are
This
using,
is the other.
as we are trying to
Find
lock
out
on to 3C273 with the 60-inch, Richard is going for
M87,
M80 7.
which is the other one with a black hole and a jet.
All right. So with
But
the
it's
refractor,
so tiny, I don't know if I can
yeah.
do it any justice. This is not going to M87, right?
No, we're going to the quasar.
Yes.
But we're not going to spend too much time there, I don't think. Oh, I see two
Two
things.
things. Hopefully they're not Castor and
Ooh.
Pollock, in which case we're pointed wrong.
So as Tim pointed out, it is a speculum mirror.
Here we
actually.
are.
Okay.
That's it.
Whoa.
We got it. Yep.
Lord Ross used the Leviathan to see the spiral structure.
At the bottom, right?
I think it's the one on the right, actually.
One of the room.
The one on the right.
So right here, this one?
Yeah. If we actually increase the exposure a little bit and maybe get another star in there, we'll know for sure.
So there are two stars on the left-hand side, and the one's kind of in a vertical line.
Yeah,
And the one on the
so-
right-hand side is the quasar,
I believe so, yeah.
a quasi-stellar radio source, which you can also see in the visible.
Okay, are we seeing any other stars in the field that might give us...
140 billion trillion miles. You know, Tim, at that distance, a billion trillion, just, you know, it's just many zeros. My brain can't comprehend that.
Yes, yes. Because, I don't remember. It was that kind of client who would get excited about...
Just saying they saw it.
All right, so if anybody watching is a little perplexed, it's like what we're getting all excited about. It doesn't look like anything other than a star. Yeah, that's it, because we can see this other star up there now. So this is making a triangle, kind of a right angle triangle. The star on the right is not a star at all. This is a galaxy, or I should say the very center of a galaxy that is 2.4 billion light years away. And the reason we can see it is because this galaxy's center has a massive black hole at the center, and it is, well, I shouldn't say it's currently eating a lot of, because this is, after all, 2.4 billion years ago that we're seeing this. This light has been traveling for that long. But 2.4 billion years ago, this galaxy's black hole was chowing down on gas accreting around it, and that gas, as it was spiraling in toward the black hole, heats up to incredible temperatures, and all the way up to like, you get X-rays, gamma rays, the whole thing. Oh yeah, you got it. And it just makes an incredible amount of light, and so we can see it, you know, that far away.
That's the jet.
That's the jet right there. All right, so there it is. 3C. Is Tim happy? Is he jumping for joy?
He says that, Okay, he says that it was the first quasar to be optically identified. And we have the Center for Excellence of Dark Matter. They used an 8-inch Meade LX200 from the Adelaide University Observatory to measure 3C273's redshift for student project many years ago, just a transmission grading. So very low resolution. Absolute magnitude of -27. Wow.
Yep.
How high are these incredible temperatures?
Oh gosh, I don't know, but it's got to be in the millions of Kelvin, right by the. Well, maybe not. Let's see. I think that's a Google question.
Yeah.
All right.
Yep, Tim's happy.
Tim's happy. Good.
He
Okay.
just wrote happy.
Oh, so that's what's causing that.
Yeah. So we're going to now
It
do
was
our.
recognized as a variable star already in the 20s and 30s? I'm not
It's a
sure.
little noisy, but
Well, it is a 12th magnitude star or quasi-star. So you can see this with telescopes. It's not, but it is like one of the most distant things that you can see through a telescope. All right, I think we're
That's
going to
pretty
move
cool.
on to our last object,
Our last object,
which is M87, please.
M87.
So we're going to see a more close-by version of what you just saw. And, okay, Richard's got it in his refractor already. So M87 has been in the news not too long ago because they imaged the very core of this galaxy with something called the Event Horizon Telescope, which is a bunch of telescopes that are all across the Earth working together in what's called an interferometer, and that way they can get incredibly fine details. They can zoom in way, way, way into it.
right there.
We'll look it up in a sec.
Yeah.
And they were able to take a picture of the black hole at the center of this galaxy. Or I should say, they were able to take a picture of the
Absence of everything
essentially almost like a shadow that the black hole is casting on the accretion disk that's going around it. So,
That looks like it's right there. See?
oh no, you're right. I'm sorry. Those are galaxies.
Yeah.
Yeah. So right where Richard is pointing his mouse in the center,
Can I zoom it in a little more?
you can try.
Yeah, right there.
Yeah, there it is. So that, what he's pointing at, is a jet of material that is coming out from the center of that black hole. And I shouldn't say it's coming out of the black
I was
hole
gonna say, yeah,
itself.
wait a second.
It's not coming out of the black hole. It's coming out of the vicinity of the black hole, and that's because of all the interesting physics that's going on around that black hole, and
As
involves
material is being
pulled in
gravitationally into the black hole.
Yeah, it turns out that the black hole can't bring in the magnetic fields. Black holes can't have a magnetic field, and so that magnetic field has to go somewhere. And I think the best idea is that it gets spun up and material gets flung out from the center around the black hole along these magnetic fields, and it's charged particles. They like to follow these magnetic fields. Okay, we're going to rotate the dome. So we're going to also now go to the same object with the 60-inch, where we're going to be able to zoom in a little bit more on the interior of that. What's putting me off is that you're so much lighter out than we were.
Yeah, when you come down to this, that's what that is.
Yeah, and so now this is the zoomed out view, and you can see, by the way, this galaxy that we're looking at is a giant elliptical galaxy. So you're not going to see spiral arms or any of those grand kind of structures. This is probably the result of several galaxies crashing together and forming this sort of mess. And there we are. We have a view of it through the 60-inch, and we'll pump up the exposure a bit. And
Centering it a bit too.
oh, and we're going to center it, of course.
Okay, there we go.
Stack that.
I don't think
No, we're not going to.
we're not going to be able to stack much of anything.
There will be no stacking here tonight.
Nothing to fix on.
Wider field of view.
Stacking.
It would be nice, but it's just.
Ha ha ha.
So is that showing up over there though? I guess.
Yeah, you're seeing it. We're seeing it on the
Okay.
YouTube.
So it's right here.
Yeah.
And so, while we're not seeing the black hole itself, we are seeing a direct consequence of
The
the existence
of
of
the black hole.
a massive and yet very compact, small object at the center of this galaxy.
Brighter works better
The
for
background
YouTube.
is noisy.
Yeah, but not on YouTube.
Okay, good.
Can we see it?
It's faint but observable. So Tim says that he left the card in front of the passenger seat.
It's there.
Okay.
I have it.
Okay. Tim, he's got it. If you didn't hear that. Again, the crow flies at midnight. Like, I'm just like, it's just. Interesting things.
And the black hole at the center of M87 measures in at about 6 billion times the mass of a sun.
Oh, you can see that jet on the YouTube.
You can
Yeah.
see it right
Yeah,
here.
today, it's good.
I'm surprised that this, we got a test without the focal release or something.
So, yep, they're telling us that they can see the jet in the YouTube feed.
Yeah, I
All the
wonder.
way down to Australia. Woohoo!
Are we 10 seconds medium? Yeah, it's
Bending forward.
probably. Well, bending's not doing anything, I don't think.
Yeah.
I can see it
Can you see
Well,
it now?
we could
Can
see
you
it a little
now?
bit. We could see it a little bit better last night, I thought, but conditions.
No one needs to hear that.
No one needs to.
Yes.
It's a beautiful evening of
Yes.
observing tonight.
Well, we could always look at the picture.
Actually pretty good.
I have to say, the temperature is much nicer tonight than it was back in February, where I don't think my jaw was working properly because some of the words coming out of my mouth were not the ones my brain had formed. Tonight is cool, but very pleasant.
Yep.
Ooh. I might be able to do that.
All right.
Should we just play a little bit more?
Okay.
It doesn't look as impressive as I know it is.
The issue we have is we will work with it. Our eyes are dark adapted more. So we're working on it on the screen, getting, oh, it looks good here. Then it doesn't translate well to somebody in a lit room on YouTube.
Yeah, right, on the YouTube feed.
I'm gonna try a high gain just for giggles.
Just for kicks.
Yes, because it's right there.
It's right there. It's looking not bad.
It's also interesting that because it's a different type of telescope, the image is actually flipped.
Oh. I was about to say that didn't help. That was
So
great.
what was pointed down in the other on the refractor is actually going up on the 60-inch.
Oh, sorry. Come on. The user interface for this is a bit.
clunky. That's what I wanted.
I don't know. Maybe the seeing's not great now. It's hard to say.
I'm gonna get the screen out of the.
Yeah, we're not talking about the HST tonight, Tim. He's like, yeah, on Earth it's hard to compete with the HST. Yeah, go away.
Yes. Give me a 6-inch refractor in space and I'd be happy, yes.
Yeah, anything in space.
Anything in space. Small is good.
Away from LA.
Yes.
Yep. So do we have a launch date for James Webb?
Every time we talk to them, it's 2 years.
It's Halloween, isn't it? It's October 31st now.
Interesting.
This year.
This year, yeah.
Yeah.
That's what I've
Well,
heard. That's the last I heard.
knock on wood. Gotta be wood here somewhere. Yeah, but right, every time you talk to them is 2 years from now. It was originally supposed to launch in
Oh gosh.
Does Tim know?
2007. Oh, Tim will probably know. All right, Barbara can see it in the YouTube feed, the jet.
Yeah, it's there.
And gentlemen, it is 10 o'clock.
It is 10
It is
o'clock.
our witching hour. So is that the best view that we're gonna get?
Can't we stay?
Oh, can't they stay and play some more?
Well, I'm trying to see if I can bring up M13. And I might be able to.
How low is that?
Well, I am going to officially bring our, not that you can see me
Oh, here,
because
I'll
all the
turn it
lights are
on. Oh,
turned
there it is.
off, but I'm going to officially bring this live stream to an end tonight and let these guys play around on the telescope a little more if they want. We will be back in 2 weeks' time, which is, oh my goodness, the
Wow.
18th? The 18th of May. And that will be the last in our series of virtual star parties that will be brought to you with the joint Glendale Community College Mount Wilson partnership. I'm not sure what's going to happen over the summer. I hope to be back. I think we all hope to be back doing more virtual star parties. But I should possibly have more news for you in 2 weeks' time with regards to that. But thank you very much for joining us this evening.
If you want to flip to the other one real quick.
Oh,
That's
and
M13.
M13 is in our view. There we go. So Richard just needed to put that out there. But thank you for joining us this, Halloween 2021 is what Tim said for the launch of
Hercules, there it is, that's gorgeous.
JWST.
I knew he would. Tim says Halloween 2021.
Yeah. Yeah, there we go. All right, such excitement here at the end of our live stream this evening. Well,
I just bumped the
that's
brightness
not
notes
where
and
we
all
wanted
the
to go
stars
to.
went
Back
back.
here. Anyway,
did
thank
better
you very
tonight.
much for joining us,
Then you got
I
and
felt
good
like I
night.
did better
You did fine all times.
That's true. It's really comfortable.